This class we're going to learn about vectors. The key here is to understand the difference between two concepts. One is vector and the other is scalar. So what's the difference between them? A scalar only has magnitude, but a vector has both magnitude and direction. The core distinction between them is direction. So why does direction matter? So for example, if you walk 3 meters, but you clearly specify whether you walked 3 meters to the upper right, lower right, or left, and that's a vector because you've indicated both the magnitude and direction. And the scalar would be simply saying, I walked 3 meters without mentioning the direction. So this is a very important distinction. If you focus on this, you will find that force, acceleration, displacement, and velocity can all be described with both magnitude and direction. If you don't include direction, it becomes distance, which has no direction, or speed, which also has no direction. So things like the magnitude of force or acceleration, when considered without directions, are scalars. And these are 4 main comparisons between vectors and scalars at this stage: force, acceleration, velocity, and displacement. And make sure you understand this very well. And the textbook also introduces a simple concept called frames of reference or reference frames. So what is a reference frame? This often comes up in exams. For example, if I gave you an expression like s equals t cubed plus t squared plus 1, so it means a displacement is a function of time t. The key here is to determine where the origin is. For instance, I could set a coordinate system and I'll make a origin point O here. So when time is 0, the displacement s is 1. So it means it's not starting from the origin, it's starting from the point s equals 1. So this highlights the importance of a reference frame. It's rarely tested explicitly, but you need to pay attention to what point is used as the reference or starting point. And the textbook also mentions something similar to polar coordinates from pre-calculus. What are polar coordinates? Let's just quickly review. First, take a point on the xy coordinate system of 1, 1. And this means moving 1 unit to the right and 1 unit upward to reach that point. But is there another way to reach point A without moving right and upward? Is there another way expressing this point? And that's where polar coordinate system comes from. You can go directly, and so far using the Pythagorean theorem, you can see the length of OA is 2 to the power of 1/2. But just going the magnitude isn't enough. We also need the angle. So we can use tangent to find the angle of theta is 45 degrees. And so this is a polar coordinate representation of A. Its magnitude is 2 to the power 1/2, and its angles is, let's use radians, pi over 4 radians. So this is how we express point A in polar systems. In physics, we use these ideas too. For example, if a Newton is 2 newtons at an angle of pi over 3 radians, we could also break it into components. So its horizontal components using our trigonometric functions, it will be 2 cosine pi over 3. And for its vertical components, it will be 2 times sine pi over 3, a Newton as its unit. So we could break it into components. And these black components if they are combined together, they're equal to the original red force. And this is very useful for analyzing forces. So for example, if you have three forces at different angles, let me just show you this one, 45 degrees, and this one for 60 degrees, and this force is perpendicular to the x-axis. And how do you combine those forces together? You can use the ways we learned before to compose each into horizontal and vertical components. And let's just see, for the right force, we can decompose it as F1 times cosine 45 and F1 times sine 45 as the vertical and horizontal components. And under this situation, we can erase this force away because they are equal to each other in physics. And we could also decompose this factor as F2 times cosine 60 and F2 times sine 60. And then you can combine them on the horizontal and vertical direction to get the final resultant force. This method applies not just to forces, but also to acceleration, velocity, and displacement. And now let's talk about vector addition. The most basic method is a parallelogram rule. Say vector A plus vector B. You can combine them as a parallelogram and then connect the diagonal. So A plus B will equal the vector C. But we don't use it quite often. A better way is to decompose each vector into components and add the components separately and then recombine them. For example, let me just give you a coordinate system. And you have a force of 2 newtons at 60 degrees. And also another force of 2 newtons at 30 degrees. So you can decompose both of the force. For the first force, its horizontal component is 2 times cosine 60, which would be 1. You can use your calculator to count this. And for its vertical components, it will be 2 times sine 60, which would be 3 to the power 1/2. And then you can erase the 2 newtons out because they will be equivalent to each other. And you can also decompose the newtons on the left. So its vertical components would be 2 times sine 30, which would be 1 newton. And its horizontal component would be 3 to the power of 1/2. And then you can combine them on each of their horizontal or vertical components. Say horizontally, its resultant force would be 3 to the power 1/2 minus 1 newton. And its vertical force would be 3 to the power 1/2 and plus 1 newton. And after combining them separately on each axis, you need to recombine them together, use your Pythagorean theorem, and do a length here. You can count it, and its angle can be calculated using tangent, and its length can be calculated by Pythagorean theorem. So a squared plus b squared plus b squared to the power 1/2 would be the magnitude of force F. So this is how you combine vectors. And let's go over some typical questions. First, a vector is given by its components. AX is 2.5 and AY is 7.5. So its horizontal components equals 2.5 and its vertical components equals 7.5. So what angle does vector A make with a positive x-axis? So still you can combine them together, and their resultant force can be calculated using Pythagoras rule. So you can just connect it. So the length of it would be 7.5 squared plus 2.5 squared to the power of 1/2, and you can use tangent to find theta, because tangent theta equals y over x, which would be 7.5 over 2.5, which is 3, and use your calculator using the inverse trigonometric function. So theta equals the inverse of tangent, and input the result here, you will get the angle. So it's probably over 50 or 72. I would say it's 62 if you use your calculator. Let's see the third one. A vector has a magnitude of 17 units and makes an angle of 20 degrees with a positive x-axis. And let's draw the axis. So its magnitude is 17 to the angle of 20. The magnitude of the horizontal component of the vector is. So we can decompose it into the vertical and horizontal component. For the vertical, it will be 17 times sine 20 degrees, and for the horizontal, it's 17 times cosine 20 degrees. You can just tap it into your calculator to get a value, and it's quite simple. So I would say it's probably 16, because it looks greater. In problem 5, vector A has a magnitude of 10 units and makes an angle of 30 degrees with a horizontal axis. So its magnitude will be 10 and with an angle of 30. So you see, it doesn't look accurate, because I think it should probably be looking like this, and it looks like the 45 degrees. So the graph isn't accurate all the time. So it's 10 units and 30 degrees. Vector B has a magnitude of 25 units, 25, and makes an angle of 50 with a negative x-axis. So here is 50 degrees. And what is the magnitude of resultant of these two vectors? So still, you can try to use parallelogram rule to combine them. You create a parallelogram, and then you connect its diagonal. So this would be what you're looking for. But you can't use this way to find its accurate value. So let's just use our basic components. We can decompose this into horizontal and vertical components. For force A, for vector A, it's 10 times cosine 30 as its horizontal component, and here is 10 times sine 30 as its vertical component. And for another one, it would be 25 times cosine 50, and for its vertical one, it's 25 times the sine 50. And then you can combine them on each direction separately. So for each vertical components, you can subtract them together because they're in reverse directions. So it would be, I'm not sure which one is bigger. Let me just take the left one is bigger. So the resultant horizontal component will be 25 cosine 50 minus 10 cosine 30. And for the vertical component, you can plus them together. 25 sine 50 plus 10 sine 30. And then, in order to find its resultant components, you need to combine them together, recombine them. You use the Pythagorean theorem to find the length of the black ones, and you can also use it to find the angle theta. So this is how we look and how we find the resultant of several factors. First, we decompose them into vertical and horizontal components, and second, we combine them on each axis independently, and third, we recombine them again, and finally we will get the resultant vector. In question 8, which vector represents a direction of two concurrent vectors shown below? Concurrent means those vectors are in the same planes. So you can use your parallelogram rules to find its resultant velocity. This might not give you the accurate value, but you can use it to find a rough one. So it will be looking like answer C. And let's go with question 10. On a baseball field, first base is about 30 meters away from home plate, and a batter gets a hit and runs toward first base. She runs 3 meters past the base and then runs back to stand on it. The magnitude of her final displacement from the plate is. So we can just pinpoint where she was originally, and so it's 30 meters away from home plate. So this would be the first base. And he gets a hit and runs toward first base. She runs 3 meters past the base and then runs back to stand on it. So she passes it. She runs here, 3 meters passes it, and runs back to stand on it. He runs back. So he's back to the base again. So what is the displacement of her? If you are asking distance, he actually runs 30 meters and 3 meters to the right and then 3 meters back. So the distance would be 36. By asking you displacement, we only care where he starts and where she ends. The process doesn't matter. So she only moves 30 meters as a displacement. And let's do the next one. Free response. Find the magnitude and direction of two concurrent forces shown below using the algebraic method of components. So we can use our old ways still. You decompose the first force into its vertical and horizontal components, which would be 10 times cosine 30 degrees, 10 times sine 30 degrees, and then you can erase this force out. They are substitute each other of the two forces, and you can decompose it. The forces on the left side, it would be 20 times cosine and 20 times sine. So what is the angle here? You can use a bit of geometry. So you see 30 degrees and it's 90 degrees, and overall it's 180 degrees. So from another side, the angle would be 60 degrees. So it's 20 times cosine 60s and 20 times sine 60s. So after decomposing them, you can combine them independently on each axis. So on the horizontal axis, the left one is bigger, so it's combined as 20 times cosine 60 and minus 10 times cosine 30s. And for the vertical components, because they're in the same direction, so we can plus them together. 20 times sine 60s plus 10 times sine 30s. And after combining them independently on each axis, we can do the final combination. And using a simple Pythagorean theorem, you can find the magnitude of the pink force and also the angle as well. So this is how we using the algebraic method of components to find its resultant force, and it's a really important method. You should master this as soon as possible, because we will be using this a lot in the future when we learn acceleration, forces, displacement, and some other vectors that we're gonna possibly use. And so I guess this is everything in this class, and I hope you can master these materials about vectors very well. It's very important and it's basically foundational. So if you feel this helpful, please just give it a like and share it to anyone you might think be helpful of, and I will be very appreciative. So see you next class.